Most of the supervised learning algorithms we've seen, things like linear regression, logistic regression, and so on, all of those algorithms had an optimization objective or some cost function that the algorithm was trying to minimize. It turns out that k-means also has an optimization objective or a cost function that it's trying to minimize. And in this video, I'd like to tell you what that optimization objective is. And the reason I want to do so is because this will be useful to us for two purposes. First, knowing what is the optimization objective of k-means will help us to debug the learning algorithm and just make sure that k-means is running correctly. And second, and perhaps even more importantly, in a later video, we'll talk about how we can use this to help k-means find better clusters and avoid local optima. But we'll do that in a later video that follows this one. Just as a quick reminder, while k-means is running, we're going to be keeping track of two sets of variables. First is these CIs, and that keeps track of the index or the number of the cluster to which an example xi is currently assigned. And then the other set of variables we use is mu subscript k, which is the location of cluster centroid k. And again, for k-means we use capital K to denote the total number of clusters, and here lowercase k, is going to be an index into the cluster centroids, and so lowercase k is going to be a number between 1 and capital K. Now here's one more bit of notation, which is going to use mu subscript ci to denote the cluster centroid of the cluster to which example xi has been assigned, right? And here's to explain that notation a little bit more. Let's say that xi has been assigned to cluster number 5. What that means is that ci, that is the index of xi, that is equal to 5, right? Because having ci equals 5, that's what it means for the example xi to be assigned to cluster number 5. And so mu subscript ci is going to be equal to mu subscript 5, because ci is equal to 5. And so this mu subscript ci is the cluster centroid of cluster number 5, which is the cluster to which my example xi has been assigned. Armed with this notation, we're now ready to write out what is the optimization objective of the k-means clustering algorithm. And here it is. The cost function that k-means is minimizing is a function j of all of these parameters, c1 through cm and mu1 through mu k, that k-means is varying as the algorithm runs. And the optimization objective is shown on the right is the average, or 1 over m, of sum from I equals 1 through m of this term here that I've just drawn the red box around, right, of the squared distance between each example xi and the location of the cluster centroid to which xi has been assigned. So let me just draw this in, let me just explain this, right? So here's the location of training example xi, and here's the location of the cluster centroid to which example xi has been assigned. So to explain this in pictures, if here's x1, x2, and if a point here is my example xi, so if that is equal to my example xi, and if xi has been assigned to some cluster centroid, I'm going to denote my cluster centroid with a cross. So if that's the location of mu 5, let's say, if xi has been assigned to cluster centroid 5, as in my example up there, then this squared distance, that's the square root of the distance between the point xi and this cluster centroid to which xi has been assigned. And what k-means can be shown to be doing is that it is trying to find parameters ci and mu trying to find c and mu to try to minimize this cost function j. This cost function is sometimes also called the distortion cost function, or the distortion of the k-means algorithm. And just to provide a little bit more detail, here's the k-means algorithm. Here's exactly the algorithm as we have written it out on the earlier slide. And what this first step of this algorithm is, this was the cluster assignment step, where we assign each point to the cluster centroid. And it's possible to show mathematically that what the cluster assignment step is doing is exactly minimizing j with respect to the variables c1, c2, and so on up to cm, while holding the cluster centroids mu1 up to mu k fixed. So what the cluster assignment step does is, it doesn't change the cluster centroids, but what it's doing is exactly picking the values of C1, C2 up to Cm that minimizes the cost function or the distortion function J. And it's possible to prove that mathematically, but I won't do so here. But it has a pretty intuitive meaning of just, well, let's assign each point to the cluster centroid that is closest to it, because that's what minimizes the squared distance between the point and its corresponding cluster centroid. And then the other part of the second step of k-means, this second step over here, the second step was the move centroid step. And once again, I won't prove it, but it can be shown mathematically that what the move centroid step does is it chooses the values of mu that minimizes j. So it minimizes the cost function j with respect to, WRT is my abbreviation for with respect to, but it minimizes j with respect to the locations of the cluster centroids mu1 through mu capital K. So what k-means really is doing is just taking the two sets of variables and partitioning them into two halves, right? You have first the c sets of variables, and then you have the mu sets of variables. And what it does is it first minimizes j with respect to the variable c, and then minimizes j with respect to the variables mu, and then it keeps on iterating. And so that's all that k-means does. And now that we understand k-means as trying to minimize this cost function j, we can also use this to try to debug our learning algorithm and just kind of make sure that our implementation of k-means is running correctly. So we now understand the k-means algorithm as trying to optimize this cost function j, which is also called the distortion function. We can use that to debug k-means and help make sure that k-means is converging and is running properly. And in the next video, we'll also see how we can use this to help k-means find better clusters and help k-means to avoid local optima.